there's something 500 people in whole Europe. They're called DPAC, and they've been working on Gaia for like 10, 12 years in order for you to enjoy the data. So I have to acknowledge that. Okay, so microlensing. I'm sure, I think these movies were not shown yet. Scott, is that possible? These excellent movies, I keep showing them every time, the animations here, because they show what microlensing is about. So photometry-wise, you've seen this Kaczynski curve, but here you see it all in action. Two images appear where there's a relative motion between the source and the lens. But Scott made also an excellent movie about astrometry. So this is from a point of view of a source. When you observe a source, and then there's a lens crossing the line of sight. If you were able to measure okay, of course we know we cannot see the actual images, but if you are able to measure the sum, the position of the sum of these two images, this is what you would see. The source, if it was static, during microlensing event, it would do this funny loop. Also, what's worth noticing is the source will go backwards and then quickly change the position to the other side of the loop. So this is astrometric microlensing, which was mentioned a couple of times here, but I think the animation was not shown. I'm showing it because it's very intuitive. But the size of this is 1 million second. So far, only Kailash was able to do it, to measure it, so far. But people are trying, and we're trying to do it with Gaia as well. Because Gaia is all about astrometry, of course, right? Okay, why do we need that? Of course, you've seen this slide already in my Tuesday talk, that we expect that there are black hole lenses, right? But we don't know which lenses are due to black holes. There should be something like 16 black holes every year, right? But we've seen a handful of candidates, I would say. This is the reason that in order to measure the mass, you need to measure these two quantities, right? At least we know how much is kappa. The rest, you don't know. So parallax is very easy to get. Theta E is much harder to get, and I emphasize Gaia. So we are trying to use Gaia in order to measure theta E for at least fractional events in order to measure the mass and find black holes in the end. So what is Gaia? And you've seen it already. I'm going to show the movie here. Good point. That's not an animation. That was real. That happened already 4 years ago. That's an animation. So Gaia was launched from French Guiana, as you could hear. All was said in French. And the rocket they used to launch Gaia was actually Russian. Because Russian rockets are very robust. So this is the Soyuz and Fregat combo. And the Fregat is the unit which you can see it here, which was used to put Gaia into the right orbit. So, and this is the only physical kind of mechanical maneuver Gaia had to do. Soon after launch, 2 hours after launch, open the umbrella. Umbrella is actually essentially hiding all instruments from the sun. Gaia is always having sun in the back. The sun is lighting the solar panels which are located in the back. And then Gaia, after launch, Gaia was traveling for like a month to L2. This is where L2 is. Gaia is actually going around L2. This is the point behind the Earth. And Gaia is running in an orbit around L2. All the other satellites will reside in L2 as well, JWST and WFIRST as well. And this is Gaia scanning the whole sky with these 2 telescopes. You can see that every scan scans slightly different part of the sky. Within 6 months, you have the whole sky covered at least once. And Gaia started scanning the sky. I have some pictures of the real thing here. This is before launch, of course. This is the focal plane. This is the zoom in. These are the actual CCDs. This is something like 1 meter in length. And all the detectors are here. This is the largest CCD ever flown in space. Right. So Camilla didn't show, she mentioned this, but I will show the excellent animation colleague of ours made, is that how the scanning works, right? So this is 0.7 degrees on the sky, and then this is along the scan, right? So it takes 40 seconds for an object, for the piece of sky to cross the whole plane. So the way it works. So there are these two star mappers, and each of them is is taking data from the two telescopes. There's the distance between the telescopes is 106 degrees. They're pointing into different directions. And if there is a star detected, which is brighter than something like 20 or so magnitudes, then there is a window allocated. Once there is a window, then the window traverses across the so-called AF CCDs. There is 8 or 9 of them. And then also there are the spectrographs, called so-called BP and RP, blue and red photometers. And then at the very end, there is also radial velocity CCDs. They work only for fraction of the focal plane, and also for the brightest stars only. So every single star gets this set of observation. This is just one observation. In Gaia nomenclature, we call it a transit, which could be confusing. So this is one transit. In one transit, you get 9 photometric and astrometric measurements. You get a spectrum in blue and red arm, and in some cases, you get the radial velocity. So now imagine this happening 70 times for each star, and then imagine billion stars altogether. So that's what Gaia is all about. You've seen this already in a slightly different version. This is how Gaia scans the sky. This is just to show you these two fields of view. This is leading and trailing field of view. This is the scanning. So normally it takes during one day, Gaia scans something like 1,000 square degrees. You see the time here, it's fairly slow, but it will speed up at some point. So this is the spin axis. So Gaia not only rotates, but also the spinning axis precesses very, very severely. And it is always, it is driven, the scanning law is driven by the position of the sun. So that Gaia never observes the sun, right? So this is speeded up, this is 2 years, and so now we're more or less here after 2 years in the mission, but it builds up. So you see there are some regions with something like 200 observations. There are regions with something like 40 observations. It's designed to be astrometry efficient. It's not designed for photometry or anything. These are all side products. Astrometry is the main goal here, and the clever people designed this scanning pattern in order to do astrometry efficiently. Right, so coming back to black holes, I already showed you OGLE on Tuesday, and then Gaia, in particular Gaia Science Alerts. This is the bit I've been involved in last 10 years. So because Gaia scans the sky, then the data is transmitted to the ground within, let's say, if we are lucky, within 24 hours. It's nothing extraordinary, but this is enough to do something, a side product of Gaia. We can, every day there is a new data, we look into millions of new data points and we check if there is a new object or a star changing brightness. So in that way we found already a few thousand of supernovae. And also now Gaia starts finding microlensing. So recently Gaia became another microlensing survey. This is a space whole sky microlensing survey. I will tell you more about it. But we're trying to combine OGLE and Gaia data for finding black holes. Not only finding new microlensing events with Gaia, but also using Gaia astrometry. That's the key. Using Gaia astrometry in order to pinpoint the black holes. This is the OGLE-GAIA sky. Again, you see this pattern of number of observations from Gaia, and this is the OGLE footprint. So you see in the bulge, Gaia doesn't like the bulge, but fortunately there are these SIF images which will probably be very helpful for these very crowded regions. But anyway, there will be some Gaia data points for OGLE footprints, for OGLE microlensing events. Moreover, there will be microlensing events from all over the place in Gaia, for which Gaia will also derive astrometry. So astrometry, how can we use this? So far, we don't have the astrometric time series from Gaia. It's still being collected. So what we can do so far, I've showed you this slide already. For a candidate black hole like this one, this is our best from OGLE, which was already 10 years ago. So we see this very long event with a strong parallax signal. At least parallax we already found. But the mass distance degeneracy is very severe. So from this, we can only guess mass and distance, have an estimate. So we're still not sure whether it's a black hole or not. If we had Gaia for this kind of event, if we imagine Gaia was flown 10 years ago and was collecting data for that particular event, that's how Gaia astrometry would look like. So this is the simulation made by Chris. So we've been using Gaia scientific performance as we know how it performs in order to simulate the time series, astrometric time series. And the point already discussed during a previous talk, you see that the astrometry is one-dimensional because you get the best astrometry measurements along the scanning direction, and across it's fine as for space, but it's not excellent. It's not enough for microlensing alone. That's why Gaia processes, so you get these measurements with large error bar in one direction and small error bar in other direction. But fortunately for black holes, not only the astrometric shift is large, so it's easier to detect, but also these events, they last long, so we'll have enough coverage at different angles in order to derive the size of this loop. Of course, the loop, it's not exactly the same as you've seen in Scott's simulation, because there is also proper motion. The source we observe is moving, and also there is some parallax. So the wiggling is due to the parallax, Earth motion. In this case, it's Gaia motion around the sun. So combining all these, you would expect to see this kind of trajectory. So from that, we would guess the mass and distance within the error bars, but that would not be an estimate, that would be a measurement. So far, the Gaia astrometry is just standard. Daily calibrations we derive for Gaia, it's of order of 50 milliarcsecond. It's good, but you can do better from the ground. And also, I remind you, this is all one-dimensional precision. We are now currently working on improving this astrometry using some preliminary astrometric solutions. So hopefully within the next few months, we might be able to provide sub-milliarcsecond astrometry for all the alerts Gaia has found. But it's still TBD. The final precision, as already pointed by Camila, in 2022 will look like this. This is this funny shaped precision curve as a function of magnitude. This shape here is due to the fact that Gaia is trying to be sensitive also for very bright stars. That's why it needs to apply some clever gating and changing the gain. Hence the astrometry precision and photometry precision as well. They will always show this. But generally, this is what we expect. This is actually more or less the numbers Chris was using in his simulations. So we're talking about hundreds or tens of microarcseconds per measurement. So then I was trying to compare it to W-first using the paper of Andy Gould, recent paper. This is H-band, and this is logarithmic scale, so this is here as well. I tried to do it very, very crudely here. You can see these are comparable, but W-first in principle should do like a factor of 2 or more better in terms of per measurement astrometry. So this is a good point that in principle you should be able to do astrometric microlensing with W-first. And when you have astrometric measurements, you can measure the masses. So this is also Chris's work. When you combine the ground-based photometry for long events, mind that Gaia sampling is very sparse for photometry, so that's not enough to get good estimate on photometry and parallax, but astrometry is usually longer. So you need to combine, ideally, OGLE or ground-based observations in terms of photometry and Gaia astrometry, and then you can measure the masses of black holes. And this is our candidate black hole. This is the precision we expect to get. It's of order of 10%. But for more heavy black holes, like the ones found by the gravitational waves, then the precision improves. It's a strong function of magnitude. You need a bright event, fairly bright event, to get this precision and also to break the degeneracy. Here, you don't break the degeneracy. So it's promising. It's not perfect, but there is some chance that this will work. Short break. Okay. Gaia microlensing. This is the second part of my talk. Again, you see the chart with number of observations and the OGLE footprint. And these are the microlensing events found by Gaia alone, right? So OGLE, of course, is finding all these events here in the very center. Gaia still has not many data points collected in the bulge. But in these regions here, and here, and here, in the disk, and also in the outskirts of the bulge, there's already enough data points, enough coverage from Gaia alone that there are microlensing events being found. There is one which Gaia missed. It was found by Assassin, which actually with Kasia, we were investigating why Gaia missed it, because there was excellent data for it. So it means that Gaia is still underperforming in terms of microlensing, and we're trying to improve this. So hopefully the event detection rate in Gaia, it will keep improving. These are the light curves. As you see, the sampling is sparse. These are the original Gaia data points. So there is just a handful of data points over a light curve. So if you look at this, these light curves, they remind first microlensing events from the 90s, right? So that's why we have established the whole network of follow-up telescopes, because we need to fill in the gaps between Gaia observations. And the most spectacular event we found, it's called AYERS rock. It was by accident. It was just called Gaia 16 AYE, but it's unpronounceable for me at least. And in order to remember that, we called it AYERS rock. And this is AYERS rock. If you don't know, kind of the proper name is Uluru, but AYERS rock we tend to call it. And what is it? This is the Gaia light curve, spanning last, well, essentially a year. If you looked at it, you would never tell it's a microlensing event, right? Fortunately, we found it around here. We could see a significant rise on a fairly bright star. And then we started to follow it up with, it was a very easy to observe target because it was bright. It was way in the north. It was in the Cygnus constellation. So well visible. And many people got involved in the follow-up. And this is the light curve we collected. So this is something like 20,000 data points of this particular event collected over the last year. These are different bands from blue to infrared. So what you see here, actually you don't see it very well here, but there was an increase here, and then a sudden jump down, and then again climbing up, and then again sudden jump up, and then the plateau between caustics, and then again it went down, but it kept rising again. So it showed something like 5 individual brightenings. So this is fairly unusual. This was one of the very first microlensing events ever found by Gaia, and that was spectacular, I would say. So this is the network of telescopes. This is not a complete map. It's based primarily in Europe because we're looking for kind of abandoned telescopes which have nothing to do. And also weather in Europe is really bad. But if you combine bad weather telescopes, you might happen to have a continuous coverage, right? That's the idea. But for that particular event, we also called for support from observatories from the US, from Thailand, Japan, from all over the world, actually. And I will tell you one story here. When so that was the model at the moment of the when we were approaching the fourth brightening. That was the caustic exit. So we knew it will happen, right? We were trying to predict when exactly it is going to happen. So the model prediction was saying that the caustic exit will happen on 21st of November, 2 a.m. UT. We started a Twitter hashtag, and then many people started following it. This hashtag you see in many languages. People were really getting excited over one night. And then the data we collected were not in agreement with the model. So the actual peak happened a few hours later, something like 16 UT, which was quite fortunate because we collected a lot of data during the peak, because the peak happened over Europe, and it was clear night everywhere. But anyway, it showed that our model, which was reproducing the caustics fairly well, was not enough, right? So we had to include the kind of the full battery here. So this is the model we have at this very moment. So this is a preliminary full Keplerian orbital solution for this binary lens. What it means? So you have the parallax. This is a long event, right? Like it's lasting like a year. So you have to take into account the Earth motion, well, Gaia motion, or an Earth motion. So this is the trajectory of the source, and this is the caustic of the binary. But binary was rotating when we were observing it, right? So you see the rotation of the binary, not only rotating in the plane of the sky, but it was also rotating kind of in the radial direction, right? So the orbit was changing. So we had to include all that, and only then we were able to reproduce the full model, which also predicted this fifth brightening. So these are the parameters of the model, and this is the preliminary solution we have for. So we solved it, right? We think we solved it. So it's not a black hole. That was disappointing in the first place. But anyway, it shows a capability of Gaia that you can measure a mass and derive period and inclination and eccentricity. You can learn everything about this binary system from microlensing, right? Also, for this one, we will have an opportunity to derive astrometry. As I said, we don't have it yet, but this is the predicted astrometric path for this particular model. So in terms of binary lensing, you have images appearing here and there, disappearing, being destroyed, and so on. So astrometry-wise, this is wild. This is just crazy. So you see the centroid jumps when there is a caustic entry or caustic exit. It changes the position very rapidly from one to another. So these are still the predictions, but these are the moments we observed it with Gaia, and because this was very bright, we'll definitely have Gaia measurements for this one. We just have to wait for the astrometry to be computed. And also, there is a possibility we might be able to measure space parallax, like people do with Spitzer. Gaia is way closer than Spitzer. But during this fourth caustic exit, this is the coverage. You see the finite source effect very nicely here. We were very fortunate that Gaia also observed it at this very time. So there are these two telescopes observing it. And these observations, they have different slope and different amplification. This still might be due to different filters, but clearly you see that there is different slopes, so magnification changes differently. So that might be a possibility to detect space parallax from a very nearby satellite, which is just in L2. To be perfectly honest, a few hours before this, the guy went into safe mode, like Kepler did for a microlensing event. But fortunately, our people in ESA, they knew that we were expecting this event here, so they put a really high priority to fix it, and they managed to fix it on time. So we believe this data is robust. But that was really, so you see these were just a matter of hours. So this was it looked like a scenario like from a Hollywood movie, what was going on. You've seen the data release scenario. I'm not going to repeat that. And actually, I will just point you to the archive website where all the Gaia DR1 data is available. The astrometric measurements will come in 2022. unless we will be able to include good astrometry, better astrometry, at least for the alerts GAIA is releasing. Not for all the sky, but for the microlensing events and the alerts. So to summarize, GAIA will soon provide 3D map of the Milky Way with all the measurements and so on. All data will be public in 22, so which will be soon after your PhD. So get ready for that now. GAIA sampling in the bulge is too poor for microlensing in general, but GAIA finds microlensing events in the Milky Way disk in particular. And astrometric microlensing from GAIA will only work for brighter events, but there is also possibility for space parallax. And WFIRST should have astrometric microlensing capability, which will be great for black holes. Thank you. No, that's significant. That's a good question. So in DR1, the positions were derived for whole billions of stars, but the parallaxes in proper motion, were derived only for. It was a combination between Tycho and current GAIA measurements. So Tycho was very limited. It was only 2 million objects. So that's why DR1 contains only 2 million parallaxes, while DR2 will rely on GAIA only. So it will be a new catalog. It will be independent from DR1. It will have a new source list, so it will be more complete, as Camila was already saying. And the parallaxes and proper motions will rely on GAIA only. So there will be more of them, because there will be a whole billion. I'm not sure about accuracy, because with Tycho, you had the precision of Tycho was bad, but the time baseline was huge. While GAIA, you have short baseline, but you have better accuracy. So I don't know how to. Thank you.